Welcome to Maths with EJD. In this video, I'll be talking about generating functions in combinatorics. So far, we've talked about introduction to generating functions. We've looked at ordinary generating functions. In the last video, we looked at exponential generating functions. So here, I want to see how generating functions apply to combinatorics. I mean, we've seen that combinatorics is one of the superpowers of generating functions, right? So let's see how this would go. Now, we know already that generating functions are powerful tools in combinatorics for solving problems involving recurrence relations, counting partitions. I mean, this whole thing can be useful in computing, computer science and all that. Counting partitions and subsets and subsets. Okay. Now, having said all of that, can we see some of these things specifically? For instance, can we look at solving recurrence relations? Solving recurrence relations. So, generating functions transform recurrence relations into algebraic equations. Into algebraic equations, making them easier to solve. Okay. Now, let's see an example in alignment with this. So we have an example related to Fibonacci sequence, which is a very popular sequence in mathematics, in biology, in computing. Fibonacci sequence. Okay. So the Fibonacci sequence, which is given by Fn equals Fn minus 1 plus Fn minus 2, Fn minus 2 with F naught equals 0, F1 equals 1. All right. So we can now define the generating function. Define the generating function for this. And it is given as we have g of x equals summation from n equals 0 to infinity for Fn, x raised to power n, first of all. So the next thing is, if we multiplying the recurrence, by x raised to power n and summing. So that will give us so that will give us g of x equals x g of x plus x squared g of x plus x. Okay, multiplying the recurrence by x raised to power n. So that's talking about like this place now. So we have so if you multiply this by x of n and you do the summing, you get g of x here. Since this already gives us a pattern for that, okay, we get g of x here. Then for fn minus 1, right? So you have x g of x, and for fn minus 2, you have x squared g of x, and then finally plus x. So here, our focus is on getting the g of x out. So to do that, we know this is g of x minus x g of x minus x squared g of x. And all of that is equal to the x that is left there. Okay. So what that means is that we now have g of x into 1 minus x squared, and all of that is equal to x. So that means that g of x alone is equal to x all over 1 minus x squared. And that's what we have as the expression. So that's solving recurrence relation for Fibonacci sequence. This is what we end up getting. Okay. Hmm. All right. So that's about solving recurrence relations. Now let's talk about counting partitions. That's another capability this has. So counting partitions. Did I number that? Okay, I did not number. So I just write now. So this is counting partitions. We're talking about counting partitions, generating functions, encode the number of ways to partition an integer n using a set of integers. So we can have an example in that case. So, and that talks about partitions into distinct parts. Partitions into distinct parts. Okay. So the generating function, the generating function for partitions, into distinct integers, is g of x equals all the products from k equals 1 to infinity of 1 plus x raised to power k. So that goes. And then we also talk about counting subsets. Counting subsets. So that's the third application of this in combinatorics. Counting subsets. You know, we're talking about generating functions in combinatorics, some applications of generating functions in combinatorics. So talking about counting subsets now. Um, generating functions, simplify subset counting problems, subset counting problems, especially with constraints, especially with constraints. So an example of that would be this. Talking about Catalan numbers. Catalan numbers. So Catalan numbers count structures like valid, valid parentheses, expressions, or binary search trees, trees. So the recurrence relation, the recurrence relation translates the recurrence relation, okay, the recurrence relation, which is Cn equals summation from k equals 0 to n minus 1 of Ck, Cn minus 1 minus k, actually translates, this translates into the generating function, to the generating function, into the generating function g of x equals summation from n equals 0 to infinity Cn x is power n, which also implies that g of x is equal to 1 minus square root of 1 minus 4x divided by 2x. Okay, so that goes that way. Okay, so in conclusion, to conclude that we see that generating functions offer a systematic method for solving combinatorial problems involving recurrence relations. Partitions and subsets. Recurrence relations, partitions, and subsets. So with this, right, we can solve problems involving Fibonacci sequence Catalan numbers with confidence and clarity. So in the next video, I think I'll be talking about um generating functions in probability. Just like I said in a previous video, I came across generating functions for the first time under probability, and you don't want to miss any of that. So subscribe to the channel, hit the notification bell, so you can always get alerted each time a new video is released. Then comment, let me know how helpful these videos are. Let me know if you have a problem I can solve for you, or a topic I can teach to clarify things for you. And of course, like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.